I'd like to thank the organizers for giving this nice opportunity to give a talk in front of you. So, today I'll be telling you about dense suspensions, jamming in dense suspension. So, if we take some simple liquid and put some solid particle at very high volume fraction, this simple mixture is called a dense suspension. So, many of these systems have remarkable ability to show a force adaptation, like more specifically, they show a force-induced reversible liquid to solid transformation. So, such force-induced changes can be under any kind of force, basically, like you can have compressive force or extensile force. Basically, like the origin of this effect is uh, basically like all these deformation modes. This is linked to shear deformation. So, you can see that if we shear the suspension, it solidifies, and if you stop shearing, it goes back to the initial liquid-like state. So this is the dense suspension of construct particle in water. Okay. So due to this remarkable property, these systems are being used uh, uh, as like for designing flexible shock absorbing materials. These are few examples. So these are some Kevlar fabric treated with dense suspensions of silica particles, and you can see that
As you can see,
you can
it's
design
impossible
crack-proof
to puncture
material
through
without
the material.
compromising the flexibility. Actually, and it can deflect bullets and also like deflect hunting arrows, but this is still a flexible material. These are other potential applications, and which has been summarized in this review recently. So you see, like these are all transient response, but unfortunately, the transient dynamics of this reversible solidification is not well understood. So, for example, there are many fundamental questions which are unanswered, like what sets the upper limit of stress response, or like when you have a solid like jam state, so how quickly it can go back to the liquid like state. So, we'll address some of these questions, and by studying transient stress relaxation in this system. Uh, yeah, so this is the system we study. We synthesize these monodispersed polystyrene particles. The diameter is approximately 2.6 micron. In large scale in the lab using a technique called dispersion polymerization, and we disperse them again at a very high volume fraction in a non-evaporating solvent, PEG. Okay, and this is the schematic of the experiment. So what we do, we take this suspension and we apply a step strain deformation, and we study the stress relaxation in this system. So these are the results basically for different step strain magnitude. You see that as we increase the step strain magnitude, the peak stress increase and also relaxation times become slower. But you notice that this is pretty fast relaxation. Actually, the entire process completes within a second or within few seconds. And the solid lines are the fits to this function, which is the power law cut off by a stressed or compressed exponential, because this beta value is greater than 1. Um, so now, interestingly, if you focus on these large step strain magnitudes, we get a two-step relaxation. So your peak stress goes up, but you see like there is a power law regime and there is a sharp step, and then there is another part. And this step is a log-log scale. So this step can be very significant. For some cases, it can be more than one order of magnitude. Okay. So now, so from these we define two time scale basically up to this step. Before that, we define a time scale that is tau f, the fast relaxation time, and the remaining that slower part is tau s, the slower relaxation time. Now, to see what is going on, we use this boundary imaging. This is the schematic setup. So we put the dense suspension between these two plates, which are rotating in opposite direction. This is the actual setup in the lab. So you put the sample in between these two plates and you illuminate the boundary, and then you image the system. The particles are opaque basically. We cannot look inside the sample. So the motivation behind this kind of imaging is, it is well known that for this shear thickening or jammed system, like under deformation, they so the particle pack, they soil, and then that pack actually after soiling it competes with the liquid air surface tension in this case, and they protrude out of the boundary, and one can image. So this is the typical boundary image we get under shear. So you'll okay, let me just play it. So you see that all the particles protrude out, and there are these. Okay, let me go back once more. Okay, so what you'll see that there are very bright spots in the system, and in the background there is these protruding particles which are not so bright, and you will notice that those bright spots are linked to the plasticity. So you'll notice that during the stress relaxation, uh, the first part, those plastic spots will relax first, and then slowly these other particles, they will relax, and eventually goes as the system goes back to the liquid like state, the relaxation becomes complete. Okay, so now what we did, we just plotted the intensity as a function of time for these very bright spots which are plastic centers. So where we got a two-step relaxation, we considered hundreds of such spots. You can see that there are two-step relaxation, and from here we define two time scale. This plastic center relaxation time, that is the first step, and after that, once these spots disappear, that is the dilation relaxation time scale, which is, if we take another region which doesn't have a plastic center, it just shows a single step basically. Okay, so now we compared the time scales uh, with the stress with what we got from stress measurement. So we found that this plastic center time relaxation time matches very well with the fast relaxation time scale, whereas this dilation relaxation time matches with the slow relaxation time scale for wide range of volume fractions actually that show jamming. So we conclude that fast relaxation is due to localized plastic events, whereas slow relaxation is the dilation. And there is interesting dependence. If we vary the solvent viscosity, you will see that the fast relaxation doesn't change, but slow relaxation changes. It becomes slower as you increase the solvent viscosity. So this fast relaxation time is sensitive to local environment, whereas slow relaxation is more sensitive to global variation basically. And okay, so I'll conclude that we showed that there are two distinct stress relaxation regime in shear jam dense suspension, and there is a nice correlation between this imaging experiment, that plastic events give rise to fast relaxation, whereas dilation gives rise to slow relaxation, and we have confirmed such mechanism. Now, these systems show interesting memory effect that I haven't covered. So one interesting point that we'd like to pursue is in future is like in other dense systems like glasses and all, they also show this highly non-exponential two-step relaxation, but over much longer time scale. Here the relaxation is over within few seconds. So what is the connection? That is an interesting question. So all the experiments are done by my grad student Sachidanand. This is my lab, and I acknowledge RRI and SERB for funding. And this is the reference for this work. And thanks for your attention.
Can I ask? Sorry. Yeah. So why do plastic deformation look like bright spots?
Yeah, that's a very good question actually. So what we think is like at that plastic events, first of all, like why they are plastic. So we found that if you apply higher strain, then they kind of like join together and create this line of fracture. Okay, now why they are more bright? So the answer is like they have this excess protrusion. So there is although this is not a crystal lattice, but this is disordered material, but when you shear, there is some defect that eventually pushes the particle at the boundary outside. So there might be such defects inside that we cannot probe. We can only probe very close to the boundary. So that excess protrusion scatters light more strongly. That is we verified also, like your focusing will be different if you try to focus those spots separately, they get focused earlier and you have to go inside for it.
And do they also occupy spaces at some defects, albeit in 2D image that you see? So are they like more localized close to defects or something?
No, actually, see, although this system is the particles are fairly monodispersed, but it's a disordered packing. So we like after you create those plastic centers, or like after they relax, we plotted this G of R basically. G of R doesn't have any signature, but now if you look at the local structure, you couldn't find any correlation till now because it's a kind of disordered packing everywhere. So identifying defect is difficult. So
The number of these
yes, yes. So that they are sensitive to strain magnitude, but you have to be careful. If you go to very high strain magnitude, they can merge and create a fracture. That is interesting, but we don't want to probe that region in this work. Yes.
This polycrystallinity, you have this grain boundaries. So how they correlates to this plastic events?
Yeah. So see, actually, these are not polycrystalline system because the it is the order is extremely short range because G of R is almost liquid like. So you can think about a disordered system, but maybe it is interesting. Like if you allow some degree of crystallinity, like if you have a polycrystalline system, but in this system that the order is extremely short range. So this is not a polycrystal.
Yeah. So before these formula relaxation type sets in the case, it seems to grow at a very short time.
Uh-huh.
What is the origin of that?
No, no, that is because see, that is the like we are applying shear at that time. Uh, so that is a good observation. So actually, it is limited by the resolution of our instrument. So we found that when you set some step magnitude, the instrument takes around 50 to 60 millisecond to go to that step. So during that time, that growth happens. But yeah, I mean that is a transient regime. Yeah.
I have a question, but in the interest of time, maybe I'll ask separately.
Let's thank the speaker.